We are back, section 7.3. We are moving on from my favorite topic, trig identities. We're still going to see them though, but now we're really going to look at the culmination of all of our study of trig, and that is using trig to solve equations. So we haven't really done this. We've kind of seen some brief examples of it, but not really. But if I'm presented with an equation that looks like this right here, example 1, then I'm going to use trig to solve for x. We're solving an equation. So 7.3 is all about solving equations. And there's a bunch of techniques that we can use to do that. So I'm going to go through each technique and then we're going to summarize everything at the end so you have a nice list of all the different ways that you can solve trig equations. So the first technique I'm going to teach you is really just very basic algebra. If it's a simple trig equation, then all I need to do is isolate x. So my goal is going to be to isolate the trig function. X is inside the function, it's what's being evaluated. So I'm going to solve for that function, and then we're going to talk about how I can solve for x. So I'm starting with 2 sine of x minus 1 equals 0. So basic algebra, I need to use inverse operations, move everything to the other side. So add 1 to both sides, divide both sides by 2. And now I have sine of x equals 1/2. So algebraically, we can solve for it like that. Otherwise, we're going to look at the unit circle. So where does sine of x equal 1/2? Sine is y. So we're really asking, where is the y value equal to 1/2? And that happens at pi over 6, and that happens at 5 pi over 6. So that's how we solve. So between 0 and 2 pi, x equals pi over 6 and 5 pi over 6. Because if I plug that in for x into this function, I will get 1/2. Sine of pi over 6 is 1/2. Sine of 5 pi over 6 is 1/2. Now, we could have graphed this function. Okay, so I'm looking at sine of x. This is pi, this is 2 pi, this is 1, this is negative 1. And where is this graph? Where's the y value equal to 1/2? Right here and right here. If we graphed that, we either know the points or we use a calculator and find those points. We see it's the same, pi over 6 or 5 pi over 6. So I'm really just solving for the sine function, and then think of it as taking the inverse sine of both sides. Solving for x, getting x by itself. So usually I will ask you for a solution within an interval, like between 0 and 2 pi. The general solution, we know that if I go around, if I start at this point, for example, and I go around the whole unit circle, 2 pi, I come back to the same point, so that's the same sine function or sine value. I could subtract 2 pi, and so on. So the general solution is going to look like x equals pi over 6 plus or minus any multiple of 2 pi. So I'm going to denote that as 2 pi k. K is any number, any integer. So pi over 6 plus or minus any multiple of 2 pi. And the same for 5 pi over 6. Plus or minus any multiple of 2 pi. Okay. And that's really all there is to it. Using simple algebra to solve this. I will go through examples. Sorry, I'm trying to decide which would be more worth your time for me to go through. I'm going to go through examples 2 and 3, and then I'll ask you to do examples 4 and 5. Okay. So let's look at example 2. I need to isolate the trig function, so I'll subtract the square root of 3 from both sides, and then divide both sides by 2. So when I'm solving for x, I'm asking myself, what value of x here will give me cosine equal to negative square root of 3 over 2? So hopefully you have this memorized. If not, We can look at our unit circle. Just remember that you will not have your unit circle with you. You will have to know it yourself. So yes, we're back to knowing the unit circle. Where is cosine, or x, equal to negative square root of 3 over 2? Where's the x value on the unit circle equal to negative square root of 3 over 2? And we see that that happens at 5 pi over 6 and 7 pi over 6. Between 0 and 2 pi. That's the interval I'm solving for. If I asked for a general solution, then you would just add plus or minus 2 pi k to each of those values. Okay? That's all there is to it. So example 3 is similar. I'm going to add 2 to both sides, divide both sides by 4, and 2 over 4 reduces to 1/2. And then I have sine squared equals 1/2. So let's take the square root of both sides. When I take the square root, I end up with plus or minus square root of 1/2. I can rewrite that as plus or minus 1 over the square root of 2, right? Because the square root of 1 is 1. And if I rationalize that denominator, like we usually do, I have plus or minus the square root of 2 over 2. So x is going to equal whatever values, whatever angle values on the unit circle, give me a sine value equal to plus or minus the square root of 2 over 2. Sine values are y values in those special points. So x is going to equal, I see, plus or minus square root of 2 over 2 in those 4 places I just circled. So all the pi over 4s. Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And that's my answer. That's it. So go ahead and try examples 4 and 5 yourself. Solve, isolate for the trig function, and then you're basically taking the inverse trig function of both sides, which we didn't get a whole lot of practice with. I know some of us struggled with that, but now is the time to understand it. Okay. So, simple algebra. It's the first way we can solve these. Another way we can solve these is by factoring. So I look at this example here and I see, example 6, here's where I'm looking. I see that I can factor out a common factor. There's a cosine of x in both. So if I factor that out, this is what I'm left with. And it's equal to 0. 0 product property. So set each factor equal to 0. So over here I have the cosine of x equals 0. What x value is going to give me a cosine equal to 0? Give you a second to think about that, but the answer is 0 and pi. Over here we need to isolate the trig function still. And so we're left asking ourselves, what x value is going to give me a cosine equal to 1/2? And that's pi over 3 and 5 pi over 3. So combined, these are my answers. At all of those angle values, I will get this equation equal to 0. Okay, so go ahead and pause, take a second, think about it. Let's take a look at example 9. Sorry, I'm trying to think about what would be best for me to show you. So try 7 and 8 yourself. Okay. Example 7 looks like it's already factored for you. So if I were you, I would just set each of those factors equal to 0. Example 8, you're going to need to factor. The leading coefficient is not 1, so that means you are going to have to use factoring by grouping. But let's look at example 9. 1 plus sine equals 2 times the cosine squared of x. I can't factor anything. There's no common factors anywhere. I think, or I am thinking, that I see cosine squared, sine squared. How can I change that to sine squared? Pythagorean identity. So I know cosine squared equals 1 minus sine squared. And now if I simplify this, I can move everything to one side and then factor. So add 2 sine squared of x to both sides, subtract 2 from both sides, and now I have something that I can factor. Again, you'll have to do factoring by grouping. This is a pretty easy one. Okay, I'm going to need to do that. Set each factor equal to 0. And then solve for the sine function. So here's sine of x equals 1/2, sine of x equals -1. So what x values give me a sine equal to 1/2? And that's pi over 6 and 5 pi over 6. And then what x values give me a sine equal to -1? That's 3 pi over 2. And so all of those x values are my answer. Okay? So basic algebra, we could factor. Of course, not all quadratics can be factored, so sometimes we might need to use the quadratic formula. Sometimes we have to use the quadratic formula. So example 10. Usually quadratic formula solves for x, or it solves for whatever variable is in the quadratic, x squared, x, or we're solving for a squared or whatever. Here, what's being squared is sine of x. So the quadratic formula is going to solve for the sine of x. Right? If this said 12x squared minus 13x plus 3 equals 0, the quadratic formula would say x equals whatever. But instead of x, I have the sine of x. So I'm solving for the sine of x here. Equals, and now it's just a normal quadratic formula, -b plus or minus the square root of b squared minus 4ac all over 2a. And we can simplify this. That'll be 13 plus or minus the square root of 169 minus 12 times 12 is 144, so 25 over 24. 13 plus or minus 5 over 24. So if I write those two solutions separately, the sine of x equals either 18 over 24, which I can reduce to 3 over 4, or the sine of x equals 8 over 24, which reduces to 1/3. So I can't use the unit circle in this case because I don't know what x value is going to give me a sine equal to 3/4 or a sine equal to 1/3. Those aren't special angles on the unit circle. So I'm just going to use my calculator. X equals the inverse sine of 3/4, and x equals the inverse sine of 1/3. Plug those into your calculator, and you will get, if you're in degree mode, 48.59 degrees and 19.47 degrees. So those are my answers. Go ahead and try example 11 on your own. I actually think you might be able to factor example 11, but if not, you can use the quadratic formula like we just saw. Okay, so algebra, factoring, quadratic formula. Lots of options so far, depending on what we're starting with, depending on what our equation looks like. And in the end, we're always taking the inverse trig function of both sides. Whether that's in our heads, not too difficult, we can find a special angle in the unit circle, or if that's not possible, we just use our calculator. Another option for us is to use trig identities. And you'll see what I mean. So here, example 12, cosecant to the 4th x minus 4 cosecant squared x equals 0. I'm going to factor out a cosecant squared. Whoops, not sure why I wrote 2 there. All right, and I mean, certainly You could use those trig identities. You could change cosecant squared to 1 plus 1 plus cotangent squared. But that would be more difficult for us. So instead, I'm just going to set each factor equal to 0. So where is cosecant squared equal to 0? We can use our trig identities now. What is cosecant squared? That's 1 over sine squared. So I'm asking, when is 1 over sine squared equal to 0? If I want, I can write that as sine squared equals 1 over 0. And then we see right away that that's not going to give us a solution. It's an undefined value. And then over on the right, we have cosecant squared. Add 4 to both sides. Take the square root of both sides. And then we're using our reciprocal identities. We flip this. Cosecant is 1 over sine, so sine is going to be, flip the right side, 1/2. So where does sine equal 1 plus or minus 1/2? And we see that that happens. I'm going to write the answer up here since I ran out of room. Pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Again, those are my solutions between 0 and 2 pi. If I wanted the general solution, then you would add plus or minus 2 pi k to each of those values. I'm going to look at example 13. You're going to do example 14 on your own. Example 13, why don't we try to isolate the trig function first? So add 21 to both sides, divide both sides by 3. Cotangent squared equals 3. I don't like dealing with cotangent. Tangent, cotangent, those are kind of difficult to think about, especially around the unit circle. So instead, I'm going to use my trig identities, the Pythagorean identity, to change cotangent squared into cosecant squared minus 1. Okay, I used my identities. Now I can add 1 to both sides, square root of both sides, and it looks like it ends up being the same as the example we just did. Sine of x is going to be plus or minus 1/2. So x is pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Okay. So go ahead and try example 14 on your own. Think about how you can use those trig identities that we've spent over a week practicing to help you turn this equation into something that you can deal with. Okay. Now, our last technique that we're going to kind of talk about, basically those are the main ways you're ever going to use to solve these equations. You're going to use algebra. You could graph if you really want to. Algebra, graphing, factoring, quadratic formula, and using trig identities. But sometimes, if you look at example 15, we see something inside the functions that is not just an x, okay? So after we use all of our other techniques to isolate that trig function, sometimes there's one last step that we need to do at the very end. So this is called a multiple angle equation. So I'm going to look at example 15. I'm going to solve this just like we did. So simple algebra in this case, add 1 to both sides, divide both sides by 2. So sine of 3x equals 1/2. So when I'm asking myself, where does the sine function equal 1/2, I know that's pi over 6 and 5 pi over 6. But that's what the sine function has to equal. But what I'm actually solving for is x. What's inside the sine function is 3x. 3x equals pi over 6 and 5 pi over 6, because when I plug those angle values in to the sine function, I will get 1/2 back. So now I solve for x. Divide both sides by 3. X is pi over 18 and 5 pi over 18. So I hope that's really straightforward. It's the same thing that we've been doing the rest of this section, except at the very end we have one last step. Maybe it's 2x equals our angle values, or 4x equals our angle values. And then all you have to do is divide to get x by itself. Let's look at example 16. Add 1 to both sides. Divide both sides by the square root of 3. Now, here's something that we didn't talk about a whole lot back in Unit 5, but it's super important for problems just like this. Where does the tangent function equal 1 over the square root of 3? Okay, now this is difficult because 1 over the square root of 3 has already been simplified to an extent. Okay, it's already been, it hasn't been rationalized, but things have already been canceled out. And so it makes it difficult for us to ask ourselves, what point are we on the unit circle? This is the same, 1 over the square root of 3 is the same as 1/2 over the square root of 3 over 2. Because you'll see that if I work backwards now, the 2's will cancel out in the denominators and I'll be left with 1 over the square root of 3. But rewriting it with those uncanceled denominators lets me very easily see, I know that tangent is equal to y over x. So this lets me see that I'm looking for points where x equals square root of 3 over 2 and y equals 1/2. So if you need to refer to the unit circle, x is the square root of 3 over 2, y equals 1/2. So I'm really looking at pi over 6. And then it will also happen where both of those are negative, since the negatives will cancel. So positive over positive or negative over negative. So pi over 6 or 7 pi over 6. So whatever's inside the function equals pi over 6 and 7 pi over 6. And so my very last step to solve for x is to get x by itself. I'll need to use inverse operations, multiply both sides by 2, and I get x equals 2 pi over 6, which is pi over 3, or 14 pi over 6, which is 7 pi over 3. Okay. Now, I do apologize. I know I don't think I've been as clear as I should be throughout this video. It's just, I know it's a long section, so I'm trying to get through this, so this isn't a 45-minute video, which I know none of you end up watching. So this is really just kind of for you to follow along the steps, and we'll definitely dive way more into this during class, okay? So don't worry if you're watching this and you're still kind of confused. I promise with practice, it gets a lot easier. So go ahead and try example 17 on your own. Same steps to solve the equation, and then your last step is going to be to solve for x itself. Okay? All right. Very last thing that we might need to do at the end. Maybe our solution gave us an angle that's not a nice point on the unit circle. In that case, we have to use inverse trig to finish solving. And we kind of saw this earlier when we looked at solving with the quadratic formula. Right? 3 over 4 and 1 over 3, those aren't nice angles, or there's not a nice angle on the unit circle that gives me those values. So here we just need to be careful. We can't forget that the restricted domain and range of the inverse trig function still applies. So if you'll recall, the inverse sine function, -1 to 1, was the domain, and then the range, the possible outputs, the angle values it could give me, were between -pi over 2 and positive pi over 2. Cosine was the same domain, but the range was between 0 and pi. Inverse tangent, the domain was all real numbers, and then the range was the same as the range for the inverse sine function. Okay. So with all of that in mind, let's look at example 18. Now, secant squared minus 2 tangent equals 4. I'm going to replace secant squared with the Pythagorean identity. 1 plus tangent squared minus 2 tangent equals 4. And I'm going to rewrite this so it looks like a quadratic. So tangent squared minus 2 tangent, subtract 4 from both sides, minus 3 equals 0. Then I can factor this. use whichever method you need to be able to factor, and then set each factor equal to 0. So tangent of x minus 3 equals 0, tangent of x plus 1 equals 0. Solve for tangent of x equals 3, tangent x equals negative 1. And now I am taking the inverse tangent of both sides. To solve for x, I'll need to put in my calculator, because here, for 3, I don't know what angle gives me tangent equal to 3. That's not a nice point anywhere on the unit circle. So I'll need to use inverse tangent of 3. And at this point, you just need to stop and ask yourself, am I allowed to plug this into the inverse tangent function? 3 is definitely in the domain of the inverse tangent function, because the domain is all real numbers. So calculator will give me an answer. And then tangent of x equals negative 1. You actually might be able to think about this in your head. Tangent is going to be negative 1 at either 3 pi over 4 or 7 pi over 4, right? Because I'll have square root of 2 over 2 over negative square root of 2 over 2, or I'll have negative square root of 2 over 2 over positive square root of 2 over 2, and those will reduce to negative 1 in both cases. But which one is in the range of the inverse tangent function? Which one am I allowed to look at? And that ends up being 7 pi over 4. Or, if you want it in degrees, since we wrote the other answer in degrees, 315 degrees. In most cases, I would accept angles, or of course I'm accepting angles. I would accept either radians or degrees. I will specify, though, if I am being particular about it. All right? That's basically it. Going ahead and try example 19. And actually, just to be absolutely sure, let's go back and look. Now that we know to check and make sure that the range has to be right for the inverse sine function, did we do this correctly? 3 over 4 and 1 over 3, those are in the domain of the inverse sine function. And then the angles I got back, 48.59 and 19.47, those are both in the range of the inverse sine function. So I'm good there. Everything worked out fine. Okay, but you should always double check and make sure that it does work. So try example 19, and then I'm going to summarize this whole section. So we're approaching half an hour, and I do apologize. What were our different techniques, our different methods for solving these trig functions? There was just basic algebra, isolate the trig function. We could graph them. That's kind of if we're desperate, though, because that's a little more difficult to do. We can factor if we're given something in quadratic form. If we can't factor it nicely, then we can use the quadratic formula. And finally, we can use trig identities to help simplify things so that we can factor, or we can use basic algebra. And then at the very end, once we've used those methods to simplify our equation, we've isolated our trig function, now we need to solve for what's inside the trig function. So usually we can just ask ourselves, what x value in here, what angle value is going to give me this trig function equal to whatever I solved for? And usually it's a nice angle on the unit circle. Now sometimes it's not. If it's not, we can use inverse trig. And sometimes it's not just x that's inside the function. Sometimes it's 3x or 1/2 x or something like that. And in that case, we just, at the very end, have one final step, like in these problems, and we have to solve for x. Okay? And that's what we call multiple angles. So that's really all there is to it, to solving these trig equations. I know that was a lot. This is kind of a long section. There's a lot of examples here. Plenty of practice, though, and we are going to spend a long time in class working on this because I want us to be comfortable with this. This is a huge topic, and really what we've been building toward for like 2.5 units now is thinking about how we can solve equations with this. So if you have any questions, please bring them to me. Otherwise, have a fantastic day. Thank you so much.